Greetings, I'm Flávia Ribeiro from the School of Arts, Sciences and Humanities of the University of São Paulo, Brazil. I'll present a study called Future Scenarios in Vehicular Emissions and the Impact of New Vehicle Technologies, Fuel and Mobility Trends in Air Quality, that me, Arissa Umezaki and Julio Chiqueto developed. Julio is part of the Global Cities program of the Institute of Advanced Studies of the University of São Paulo. This will be the structure of my presentation, starting with the context of vehicular emissions in São Paulo and the motivation behind the work, explaining the methodology and presenting some results, conclusions, and discussion. The metropolitan region of São Paulo is one of the largest conurbations of the world, with more than 21 million inhabitants, that is 46% of the population of the state, and more than 7 million vehicles, 63% of the state vehicles. Its fleet emits annually 124,000 of metric tons of carbon monoxide, 46,000 of tons of nitrogen oxides, 1,000 tons of particulate matter, 28,000 of tons of volatile organic compounds, including evaporative emissions and emissions during supply. The vehicles also emit more than 14 million of tons of carbon dioxide equivalent, and, according to Ferreira and others, contribute to half of the anthropogenic heat. The study was mainly motivated by the need to quantify the effect of public policies and urban mobility planning on vehicular emissions. In the national level, programs to control vehicular emissions establish phases of implementation of increasingly restrictive limits for emission factors. The use of biofuels, such as ethanol and biodiesel, is relatively encouraged. Flex fuel and gasoline vehicles may use gasoil, that is 27% ethanol and 73% gasoline, and the diesel also has 8% of biodiesel in it. Lately, a lot of research on biofuels is being developed. In the municipal level, some actions have been taken and a set of policies have been developed. The Municipal Mobility Plan prioritizes public transport and active modes, such as walking and riding bicycles. Recently, a municipal law gives discounts in the taxes of electric passenger cars. Another municipal law establishes that buses in public transportation need to eliminate their CO2 emissions by 2038. To achieve this goal, the bus fleet may be changed entirely to electric. Additionally, in 2019, a working group started the development of a plan for climatic action. With the help of the C40 Cities Network, aiming to have a carbon-free city by 2050, while adapting to climate change impacts and distributing social environmental improvements equally. Therefore, the main goal of the present work is to determine emission abatement for future scenarios to better inform policymakers considering pollutants, greenhouse gases, and the vehicular impact in anthropogenic heat. The influence of changes in fuels in the secondary pollutants, such as ozone, is also considered, and the future scenarios include changes in fuel, engine, and mode of transportation. The methodology to quantify future emissions is based on the tendency of the last 12 years of the active fleet. That is a concept used by the Environmental Agency of São Paulo. The active fleet is a number greater than the licensed fleet because some vehicles are not licensed, and lower than the registered fleet because some vehicles that are not in use anymore are still registered. A regression was performed for each type of vehicle and fuel. For increasing tendencies, logarithmic functions were fitted, and for decreasing tendencies, exponential functions were used. For the calculations of the emission inventories, the same methodology of the Environmental Agency was used, so the results could be compared. Regarding flex-fuel vehicles, the choice of fuel is based on the fuel price. For future business-as-usual scenario, we use the same proportion as the agency calculated in 2017. 50% of flex-fuel vehicles used ethanol and 50% used gasohol. The inventory uses a bottom-up approach for pollutants emission, except sulfur dioxide, that is calculated using a top-down approach, as also is carbon dioxide emissions. Vehicular anthropogenic heat calculations were based on the same methodology as Ferreira and others. The bottom-up approach considers the sum of the emission factor of the pollutant multiplied by the number of vehicles and the average of activity, that is the distance traveled per year, for each type of vehicle and fuel and age. Only vehicles up to 40 years of age are considered. The vehicular anthropogenic heat is estimated by the sum of the net heat released multiplied by the fuel density, the number of vehicles and the activity, and divided by the economy for each type of vehicle, fuel, and age, and then divided by the area of the metropolitan region. For electric vehicles, the net heat released only depends on the type of the vehicle. The evaporative emissions consider the diurnal phase emission, an average distance per ride, hot soak phase, and running losses. The top-down approach applies an emission factor to the total consumption of fuel. This approach was used to calculate emissions of sulfur dioxide, carbon dioxide, and volatile organic compounds emitted during supply. Carbon dioxide equivalent considered also nitrous oxide and methane. The business-as-usual scenario only considered the active fleet tendency and that the renovation of the fleet will lead to a lower average emission factor because older vehicles were bought when the limits for emission factors were less restrictive. To develop future scenarios, an interdisciplinary group of researchers discussed the trends in technology, fuel, mobility, and public policies. The potential changes selected were the electrification of buses and 40% of passenger cars, the increase of the use of ethanol in flex-fuel vehicles, representing the biofuels, and based on a survey performed by the consultancy agency Kantar, a decrease of 48% in the use of passenger cars and an increase of 23% in buses activity. The scenarios were modeled by changing vehicle activity and emission factors. To simulate the impact of emissions abatement in secondary pollutants, such as ozone, two simulations with the chemistry model WRF-Chem were performed, one using the business-as-usual scenario emissions and other using the alternative scenario emissions. The meteorology used was from 13 to 15 of January 2018. We used one domain with 200 by 200 kilometers and 1 by 1 kilometer grid. For now, the anthropogenic heat is not included, and GFS files were used for initial and boundary conditions. The emissions were distributed spatially using types and lengths of roads for each grid cell, with the help of the smoke model. Now presenting the results. This figure shows the evolution year by year of the active fleet. You can see that the total fleet is increasing, mainly because of flex-fuel passenger cars. Gasoline cars are decreasing. Bus fleet is also slowly decreasing. For the business-as-usual scenario in 2038, some pollutants present a decrease. This is caused mainly by the renovation of the fleet that causes a greater number of vehicles with lower emission factors in comparison with 2017. This result shows long-term effects of the emission control program. Additionally, as the number of flex-fuel vehicles increased and gasoline vehicles decreased, the use of ethanol is higher. This effect helps decrease emissions of some pollutants, particularly evaporative emissions, but increases volatile organic compounds emission that may have important effects on the formation of ozone. Vehicular anthropogenic heat increases in 50% and carbon dioxide equivalent in 40%. If no action is taken, the region will increase its contribution to climate change and to urban heat island effect. Considering the alternative scenario, when compared to 2017, all the emissions are lower. Electric buses and cars help decrease particulate matter and nitrogen oxides. Decreasing use of passenger cars help decrease carbon monoxide and volatile organic compounds, even with the relative increase in the use of ethanol in flex fuel vehicles. Anthropogenic heat will slightly decrease, mostly because of electrification. For carbon dioxide equivalent, this scenario presents a 38% of decrease. This is an important result for climate change mitigation. For the simulation results, here we present the concentration of ozone for January 15 for 9 a.m. local time. Here you can see that there is no great difference between the scenarios. Also for 12 local time, here there's an increase here for business as usual in this area. At 15 local time, also business as usual has an increase. Here we can see there's a difference here because of the escarpment between the coastal area and the metropolitan region. There is in a plateau. The main wind is from the northwest. Differences in ozone are minimum, also for 18 local time. This result shows that the alternative scenario is capable of reducing primary pollutants, greenhouse gases, and anthropogenic heat, while ozone is not substantially affected. During the first weeks of social isolation because of the COVID-19 pandemic, vehicular emission in São Paulo dropped, but in a way that led to an increase in ozone. But these scenarios, you can see that for business as usual and alternative scenarios, the ozone is almost the same. To conclude, we found that emission factor limitation policies have long-term results, especially if they are updated. If no action is taken, transportation emissions of greenhouse gases in São Paulo may increase. Increasing greenhouse gases and anthropogenic heat may point to synergistic effects between urban heat island and climate change extreme events. Combining actions produce better results. Ozone is not substantially affected by emissions abatement, differently than what was observed during the pandemic, and all emissions must be considered as well as secondary pollutants when designing air quality policies. The pandemic is a cause for more uncertainties in future scenarios, but the present methodology may be quickly adjusted for other scenarios. In future work, we plan on addressing the impact of increased anthropogenic heat on urban heat island circulation and, consequently, on air quality. Additionally, secondary particulate matter will be addressed as well. These are our references. We thank FAPESP for the funding and thank you very much for watching.